So let's solve numerical on Norton's theorem. We have studied the statement and the procedure to apply Norton's theorem. And now next is to apply those procedure to solve numerical based on Norton's theorem. Let me tell you one thing more once again, that Norton's theorem is actually duality of Thevenin's theorem. There is a relationship between Norton's theorem and Thevenin's theorem, which we are going to study here in this video. Now the first step is what we are going to do. We are going to step number 1. What is the step number 1? Step 1, which is short the branch AB, short circuit the branch AB, that is short AB. We are going to short this AB. See this? I have connected this and shorted this. So the short circuit element current I and will flow. We have studied this. Okay, this was the green part of the circuit, giving you idea that this was given to you. This was given to you, and this yellow one is your short circuit. When I have started solving this numerical or Norton's theorem, I have shorted the branch AB. I have shorted the branch AB like this. Okay, now see this. When I have shorted this branch AB, will that 5 ohm resistor will work? Definitely not. This resistor will become redundant. This resistor will become redundant to short circuit. What is the meaning of redundant? Redundant means it is there in the circuit physically, but electrically it will not take part. What does it mean? It means, suppose there is a current at time t. At time t is equal to t1. There is a current. There is some current coming, and this current will decide where to go. There is one short circuit path and there is a path having 5 ohm resistor. Current always chooses least resistive path to travel. All the current will bypass from this short circuit element, short circuit terminals A, B. Okay, so it will not take part in the circuit. So just we are going to remove this. Please remove, because it will not participate in the circuit as of we have short circuited the terminal AB. Now the circuit will be like this. Circuit will be without this 5 ohm resistor. One more thing we are going to do in the next, before I draw the next circuit, what I am going to do, see this, this is your 12 volt battery in series with 4 ohm resistor. Apply source conversion. And we are going to convert this voltage source in parallel with a series source into a current source, in series. We are going to convert this into a current source with a parallel resistance. Okay, see this. This is your original 2 ampere current source given. I have drawn this. Okay. Now what I have done, I have converted this. This one has been converted into a current source and parallel resistor. So current source is this. Okay, and the value of this current source will be voltage divided by resistance, that is 12 by 4 is equal to 3 ampere. So this will be your 3 ampere current source. Now that 4 ohm resistor will be in parallel with this current source. Okay, now this was before this 8 ohm resistor, so 8 ohm resistor will be here. Okay, so this is your terminal A, this is your terminal A, this is your 8 ohm resistor, this is your terminal A, and this is your terminal B, which is actually short circuited. You can see this. This is short circuited, and current IN is flowing across this terminal AB. So now, after we have applied step 1, we have short circuited terminal AB. We have removed the redundant circuit part, that is 5 ohm. We have to analyze the circuit very much clearly, that which is important for our numerical purpose, for our purpose of getting the response. Okay, now this is your circuit. This is your converted parts. Let me draw by another. This is your converted source conversion along with this parallel resistor, which is your 4 ohm resistor. Okay, now using current division rule, what I'm going to do, I'm going to write the current, that is for step number 2, short circuit current IN is to be calculated. I'm going to calculate short circuit current IN using current division rule, that is by using current division rule. I'm going to calculate IN, that is IN is equal to, IN is flowing in the terminal AB. This is very much clear to you, and this 4 ohm resistor and 8 ohm resistor are in parallel. Can you imagine this? Yes, we can imagine this. This 8 ohm resistor and 4 ohm resistor are parallel. Okay, because this is short circuited, because terminal A and B is short circuited, and this point is common to 4 ohm resistor and 8 ohm resistor. Okay, and this point AB is short circuited. Okay, so it is potential short circuited here. So IN will be equal to, see this is 2 ampere current coming from here, and from here coming 3 ampere current. So just at this point it will be 2 plus 3, that is 2 ampere plus 3 ampere, it will be 5 ampere current. So current 5 ampere is actually dividing across 4 and 8 with the rule of current division rule. See this, IN is equal to 5 into 4 upon 4 plus 8. Okay, so it is 1.667 ampere. This is your short circuit current IN. IN is flowing in this your 8 ohm resistor. Okay, so this is your resistance which is in neighborhood of 8 ohm resistor. This is the original circuit. Let me draw that circuit once again for you. That will become very much clear to you. This is your 2 plus 3 ampere, that is 2 ampere plus 3 ampere which is 5 ampere. This is your 5 ampere. Okay, and this was your internal resistance of 3 ampere that was converted from the voltage source given, and this is your 8 ohm resistor, 8 ohm resistor, and this is your 4 ohm resistor. This is 8 ohm resistor. Okay, so this terminal A and B was short circuited, and short circuit current I was flowing. So we are interested to find out current in this branch. Okay, the total 5 ampere current is flowing up to here. Now by applying current division rule, IN will be equal to total current 5 ampere into, we are calculating IN. IN is flowing in 8 ohm resistor, so it will be here 4 upon total resistor of parallel pass, 4 plus 8, so it is 1.667 ampere. IN is coming 1.667 ampere. Okay, now step number 3. What is the step number 3? Let us understand. This is our original circuit. Step number 3. Step 3, that is to find RTH. What we are going to do? Open current source, and we are going to do. We are open current source, and we are short circuiting the voltage source. This is in short. We have studied in detail in previous videos. So what we are going to do? See this. From the previous diagram, see this. This is our current source. Current source will be opened. It will be opened. Okay. So the diagram will be like this. This is opened. This is 4 ohm resistor. This is 4 ohm resistor. This is 8 ohm resistor. Now from the original circuit, this will become a prominent. This will appear in this part. Okay, that's why I have drawn this original circuit here, just to remember what was initially redundant while calculating IN. So this is your terminal A and B, and you are actually standing here. And seeing your circuit. This is your I side. You are standing here. Okay. So what you are saying? This you are saying that this is in series. You will see that 8 ohm and 4 ohm are in series, and this series will become in parallel with 5 ohm. That is, the observation is Z equivalent will be 8 ohm is in series with 4 ohm, and thus that entire will be in parallel with your 5 ohm. That implies 8 plus 4 are in series and in parallel with 5. This is your R equivalent. This is your RTH or R equivalent. Okay. So it is coming to be 12 parallel 5. Now here RTH is equal to 12 parallel 5 is equal to 12 into 5 upon 12 plus 5. 12 plus 5, which is coming 3. I have used the calculator here. 3.5294 ohm. Okay. This is RTH. Now step number 4, which is the final of this, the Norton's equivalent circuit, which is this is your this is 3.5294 ohm, and this is your 1. Now in the step number 4 we are going to draw Norton's equivalent circuit. That is, while we have calculated Norton's current and equivalent resistance, the equivalent circuit, that is Norton's equivalent circuit, will be like this. This is our equivalent circuit. This is our Norton's current source, and this is our equivalent circuit, or RN. Now there is a relationship between Norton's theorem and Thevenin's theorem, which is like this. This is the relationship between the Norton's theorem and the Thevenin's theorem. The first point is it is dual to each other, and the second point is Norton current, that is IN is equal to VTH upon ZTH. That is VTH is equal to IN into ZN. This is the relationship between Thevenin theorem and Norton theorem, which is important as far as your university exam is concerned and various interview sessions that you may face in your future is concerned. So this was all about your Norton's theorem. We have seen that Norton theorem is actually dual of Thevenin's theorem, and we have applied Norton's theorem while having a numerical. So thank you so much for this watching my video, and if you have not subscribed my channel, please subscribe it. Thank you so much, and all the best for your studies.